Is this where you got us leaving off at? Seems like it. Good. That's what I thought too. Because we did this one. Okay. So it's all about metric, and I forget who I told these stories to. I think I probably told you guys, but did I tell you the whole? When I was like in 5th grade, my teacher said that when you go gas up your car, it's going to be in liters, not gallons. Yeah. Well, guess what? Still in gallons. But liters is a metric base unit, and with liters we can do some prefixes. Okay, to say that if you have more than a liter, you're going to use these guys. More than a liter, less than a liter, you're going to use these guys as prefixes. Okay. Now that's not just for liters. It could be for grams. It could be for seconds. It's just the metric prefix that we go to say how many times more than a liter or whatever you have, or how many times less than that base unit you have. I'm going to circle 4 of these, and 4 that I'm going to have you commit to memory, and I will count you liable on a test. First is one big one, kilo. So kilo, you're going to have to memorize that anytime we're talking about kilo, we mean 1,000 times the base units. Another one is centi. Oh, not just the prefix, but also the symbol. The symbol for centi is a lowercase c, and that means 1/100th of it, whatever it is, whether it's a liter or a gram or a meter. The next one is also small, milli. The symbol for milli is a lowercase m, and that means 1,000th. 1,000th. Milli was 1/1000th. Actually, it's like this, 1/1000th. Okay. All right. The last one is underneath milli. So I want you to know micro. The symbol for micro is a Greek letter mu. Mu actually looks like a U with kind of a front end, kind of a little bit longer tail. Mu. And that means 1/1,000,000th. So 1/1,000,000th, 1/1,000,000th, 1, 2, 3, comma 1, 2, 3 of the base units. Okay, so know those 4 for this class. You might need to interact with some of the others, but all right. So this is a slide with similar information. Let me go ahead and circle the kilo. Let me circle the centi. Let me circle the milli and the micro. Okay. We'll be talking more about this meaning column. Some of you recognize that 10 with a superscript number, that's actually 10 to a power. So 10 raised to the 3rd power would be 10 times itself 3 times. 10 times 10 times 10, which is what that does. In this class now, one of the things we'll be working with are conversions, like how do you get from centimeters to inches? How do you get from miles to centimeters, that sort of thing. And we'll be working with a lot of equivalency statements. So if I hold up my hands like this, in between these 2 quantities is an equal sign. These are my equivalency statements. Okay. So here's an equivalency statement. With regard to the unit meter, if we tack on a centi means 1/100th. So 1 centimeter is 1/100th of a meter. Okay. Now, you probably won't see me do that equivalency statement because I don't like fractions of equivalency statement. They kind of drive me nuts. So I kind of flatten it out. One of the things we know about algebra or about equality like that is if we multiply both sides by the same thing, that's legit. So if we multiply both sides by 100, okay, all I'm doing here with this third line is multiply both sides by 100. Why would I do that? Well, because if I multiply both sides by 100, now this 100 cancels with this 100. I think we kind of talked about that before. 100 over 1. 100 over 1 is the same thing as 100, so I kind of do it this way. Anytime you have a term in the numerator and term in the denominator, and all you're doing is multiplying, dividing, they cancel. So I could rewrite this as 100 centimeters is equal to 1 meter. And the deal is that both of those equalities are great at stating the relationship between centimeter and meter. They're both awesome. Okay, I prefer the thought, but they both mean the same. So an equivalency statement, this is just an example of using the one of the 4 prefixes you need to memorize. We're going to talk either today or tomorrow about exact quantities. And it's exciting within the metric system. This is an exact relationship between these 2 quantities. If you're dealing within the metric system, all of those are exact. That's nice. That's nice what happens. Okay, speaking of exact, we have this other cool relationship. Now this would be between what we have, English inches and metric centimeters. English to metric. And not very many of those are exact, but we have this exact one, where 1 inch is exactly equal to 2.54 centimeters. And that's actually by definition. They set it up that way. You're like, well, thank goodness. Okay. This one's not exact. Again, it's between English and metric. Okay. 1 gallon is approximately equal to 3.75 liters. And we'll kind of talk about kind of what that means, approximate. That introduces uncertainty. And with regard to mass, English and metric, we could say 1 pound is approximately equal to 453.6 grams. Now, I'm going to go ahead and circle, just like I circled before. You have to memorize this one, if you haven't already. It's an exact relationship. You have to memorize it because we'll be using it here and there. 1 inch is exactly equal to 2.54 centimeters. Every once in a while, I'll kind of tell myself, I'll like turn it around and I said, 1 centimeter is exactly equal to 2.54 inches. I'm like, no. So anyway, if I concentrate. All right. Another thing you need to memorize. So if I circle it, you need to memorize it. Memorize this important thing with regard to volume. Now, these are both within the metric system. I don't have it with me, but I can get it. Hold on. These are so my lab is locked. But centimeter is, you guys are going to be using rulers tomorrow. So each major unit, those are all centimeters. So if you take 1 centimeter by 1 centimeter by 1 centimeter, like a box, a cube, that actually would contain a volume of 1 milliliter. And I'll show you tomorrow and then I'm going to show you. So 1 centimeter cube is 1 milliliter. Sometimes you'll see cc's. I don't know if they do as much as they used to, but in medical stuff, give them 1 cc or 0.5 cc's. That's cubic centimeter. Cc's. No. So what if they just say milliliters? I think they're going more to that milliliters, but they could. They're exactly 1 to 1. Okay, so people come to this class with an assortment of kind of scientific notation. And scientific notation is good in kind of packing up either big or small numbers. We got to do it in science because you're talking some big numbers and some very small numbers. One of the things we're going to talk about in part 4 is this idea that when you write down a quantity, this is that last point up there, you are relaying to whoever reads that quantity you wrote down, whether it's inches or gallons or liters or whatever, you are relaying to them something about your measuring device or something about how that number was calculated. The uncertainty is kind of balled up into what we call the significant figures. So an example of a number written in scientific notation. So I can just make up a random number. So for instance, if I had a big number like 72,030,000, like that. Let's say it's feet. So that's a lot of feet. So to pack that number up, and I'm going to do some examples here in a minute, you guys would probably tell me that the decimal place is right here for now. And actually, I'm going to go ahead and put like some dots around it because it's not, somebody didn't explicitly put it there. We just implied it's there because what we know about numbers. So in order to write pack this number up into scientific notation, I'm going to move that decimal place 3, 4, 5, 6, 7 places this way. So now if I put a decimal there, you're looking at 7.203 times 10 raised to the 7th power. And again, some of you are like, oh yeah, I totally got that, which I hope you do. Okay. But my point here is this is my decimal part, and this is my exponent part. Okay. And sometimes this is called a coefficient part, but I won't. There's another word that coefficient means in chemistry too. So 10 is the same thing as 10 raised to the first power. Makes sense. 10 times itself one time. Like, all right, then. If you have 10 squared, that's the same as 10 times itself twice, and that's 100. Bet you guys got this down. 10 cubed, it's 10 times itself 3 times, that's 1,000. 10,000 is 10 times itself 4 times, and that's 10 raised to the 4th power. 100,000. Okay. I bet you're all okay with that. Most people are. Okay. So when we look at this exponent part, remember that that is what it's talking about. So let's talk small now. 0.1 is 1/10, and that's the same as 1 over 10 raised to the first power. Anytime you see something in the denominator raised to a power, you can actually go ahead and flip it up into the numerator, the top of the ratio, and doing so you have to change the sign of the power. So again, I'm not a math person, but that's totally true. 0.01 is 1/100th, and that's the same as 1 over 10 raised to the second power. In other words, that's 10 to the negative second power. And it goes on. Any questions about this? Okay. So these work well for small numbers. So in other words, if we are going to pack up a small number in scientific notation, you're going to see that this power of 10 is going to be negative. All right. So this number, 455,000, can be thought of as 4.55 times 100,000. And we can take that 100,000 and pack it up, and that's 10 to the 5th. Okay. So again, I think you'll let me know if you're like, now how does that work? Because sometimes I can't tell. I'm not going to tell on your homework, but okay. All right. So let's talk a small number here. This is 0.0021 can be thought of as 2.1 times 0.001. Of course, 0.001 is 10 to the negative 3rd. So that's kind of how we end up packing up our numbers into scientific notation. Okay. So, if the magnitude is large, like this one is, you're going to end up, what I feel like is I'm going to move the decimal place over from the right to the left. I'm going to count the number of times. Okay, and as I move it, my goal is to get a number that's between less than 10, but greater than 1. Okay, and then you write that number. That's going to be what we call your, I'll just go ahead and say it. I think let's see, coefficient. This first part's your coefficient, scientific notation. And then the number of times you moved it over, if it's a large number, is going to be to the positive 10 raised to that positive power. I feel like I'm going fast, but I don't see anybody that's like, what? Slow down. So if the number's small, then you're going to end up moving the decimal from the left to the right. Again, you're going to count the number of places you move it, and you're going to move it such that you get a number between 1 and 10. And then you're going to, as you count the number of places you had to move it, you're going to take 10 raised to that negative power. Okay. All right, here's one for you. Anything raised to the 0th power, anything, in this case 10 raised to the 0th power is 1. Well, that's kind of blows my mind. I don't know, for some reason. It's just true. So if somebody tries to pull one on you and like, okay, Pat, this number up in the scientific notation, you're like, what? I can't move the decimal. Well, then if you have to pack it up scientific notation, you just write that as the coefficient, and you take that and you say it's times 10 raised to the 0th power, and you're off the hook. You've written it in scientific notation. It's kind of a silly thing to do, but anything raised to the 0th power is 1. So 10 to the 0th power is 1. It's the identity property, multiplicative property of 1, I don't know. All right. So do you guys have these now? Okay, why don't you go ahead and take a few minutes to jot those down. But before, I think, let's see what's. Gabe's raising a good point. This last one down here, because I kept saying that the coefficient needs to be between 1 and 10, and negative 4.4 is not between 1 and 10. So, you're right, I'm not mad at you. Sorry. So, my point with this last one was you can see where I kind of moved the decimal place over. Clearly 4 places from the right back to the left, so it's going to be a positive exponent of 10. And then you have to carry this negative sign with your coefficient. That's all right. You buy that?
I mean, I guess.
Yeah, we don't in chemistry and physical science in general, we don't deal with a lot of negative numbers, but I have to double check. I'll look into that, see what my wording looks like there. Any other questions? That's a good one. Okay, very good. Okay. So, let's see. These will be due on Wednesday. Do you think they cancel school when it gets to be negative? Oh, yeah, I don't know.
I think negative, well, the high is -2, and then the low is -17, then the
With the wind.
supposed to be -30. The reason why they cancel school when it's like so cold is because buses use diesel, right?
Oh, okay.
And diesel jumpies at like a certain point.
Yeah. Well, what about colleges? Forget about y'all. What about colleges? No, you're both.
There's something on Facebook that said it'll take 4 months for your bare skin to become get frostbite, -30 or something like that.
Yeah.
It's like a.
That's a danger thing.
Yeah.
Yeah.
It's something like that on Facebook, but that's Facebook. So.
Facebook's always right.
Yeah.
So, well, we'll see. But to me, one of the coolest things is to, and when I find out how you sign up to get automatic phone calls, which my husband's like, he teaches too, but he's like, I don't want them to know my phone number, but I'm like, what the heck? If you're going to call me when school is canceled, I will send. Oh, I just finished that thought. I will send everybody an email. Which if you can't get your email, you won't get my email as instructions how you sign up. But I don't know. Because remember, that's also, if I'm not going to be here for a particular day, I let you guys know. All right. So part 4, okay? I mentioned that if you have a number packed up in scientific notation, actually that decimal part there will tell you the number of significant figures for that measured quantity. So you're like, what's significant figures? What's significant about significant figures? Well, in this day and age of thou shalt not lie or whatever, when you record, like tomorrow's lab, not that you rely on purpose or anything, but tomorrow's lab, you are going to report a specific value. Like for length, it's going to be a specific, you're going to have to report your length specifically, and that you're going to relate the length that you get in centimeters in terms of a certain number of significant figures. So for instance, if your ruler, this ruler I have up here. This ruler goes to the nearest, I told you these major divisions was a centimeter, it is a centimeter, and then the little tick marks are actually millimeters. So, which is a tenth of a centimeter. And I'm going to kind of talk you through it here, but I need you to go to the nearest, you have to guess between the gradations, which is, I know it's like really not guess, but estimate between the gradations. So if the gradations are a tenth of a centimeter, I'm going to have you go to 100th of a centimeter. That's what I mean by writing down the right number, relaying the correct information about your measurement. Be proud of your measurement and relay it correctly. So in evaluating things, in sharing information, we need to be as accurate and as precise as possible. Accurate actually implies that I know what the true value is, okay, and how close am I. Precision is actually kind of well, let's put it this way. Precision is a test of how reproducible your method is. So it's possible that your method could stink, but you're very right on, you keep getting the same value, you're very precise, but you're just not very accurate, okay? Or it could be that you have a scatter of values, that if you take the average, you're right on target. So your accuracy is great, your precision isn't. So if we kind of look at a bullseye in terms of you're throwing darts, you're trying to get in the center, so that would be totally accurate in the center. Notice in this case, if I take the average of these 5 darts, I'd be like, maybe right about there. Okay, so the average isn't good. And I mentioned scatter. The other thing is the person throwing these darts, and it's probably a lot better than I could throw darts, but the person throwing these darts aren't very reproducible. So this is a case where the precision stinks too. Precision is like the scatter. Okay, here we go. Nice, tight. That's pretty impressive. But so the precision is very reproducible, but not very accurate. Okay, and this one, okay, the average of it's nice and tight, good precision, and the average of them is right in the center of the bullseye. I guess I would argue that there's one more scenario, and I'll use that last one up there. I would argue that if I had poor precision, you know, if these are, you know, the scatter of my 5 darts, my precision stinks, okay, but my accuracy is good. And that's one last scenario. So precision and accuracy. So when we do labs, there's going to be some labs that we do where we know the right answer. And so how far away from the right answer we get is actually a type of error. We can measure the error. So error actually measures how accurate you were. Okay. There's different types of error. There's absolute error and relative error and percent error, but it's all about what you got versus what you thought you should have gotten. Don't reboot my thing yet. And then there's uncertainty. There's the wiggle. There's the kind of what I call plus or minus. Are you serious? No. Oh, cripes. This is not my day. Go away. Maybe let me go. Okay. Hopefully you can see past that. I can see past that. Because if I click that, it's totally going to restart, and I don't want to restart right now. So uncertainty, the size of interval that is best represented by the measured value. A lot of times if you send away a sample for analysis, they know how rugged their test is and how the precision associated with how they test things, how accurate they tend to be for that particular measurement, and they'll give you a value. Well, it's kind of like polls. They'll give you a value and they'll say, well, that's plus or minus this. Okay. Can't make that go away, or final stuff's going to go away. So error is associated with accuracy. We have absolute error, otherwise known as absolute uncertainty, and that is just kind of a subtraction. It's like the word, I think this would be right. When I think of absolute, we do this a lot in chemistry, or we're dealing with numbers. I think of absolute value, so that's kind of like we remove the sign of it. Relative error or relative uncertainty does one last thing. In the numerator or in the top of this, to kind of assess how good you did, what your accuracy was, we do the subtraction. We take let's go. We take what you thought you should have gotten minus what you got divided by what you thought you should have gotten times 100%. So it's a ratio thing. That's so annoying, but
What was that?
which one?
Relative errors, relative uncertainties are
Unitless. Yeah, that's good. This word is unitless. The relative errors and relative uncertainties are units numbers. And what we're going to see that makes sense is because the units actually cancel out. Good question. I'm not clicking OK. So as good as we all are with our measuring devices, anytime, like if I wanted to get a distance from here to here, I wanted to write something down. To me, that looks like, let's see, these are centimeters, so 10, 20, 30, 40, 44, 44.5, I'm going to estimate 44.59. 44.59 centimeters. There's uncertainty in that. And actually, that's a good example of probably, what did I say? 44.5 was it 4.9? 5.9. I don't know, what is it? 5.9 centimeters. Usually, and I'm going to see that actually it's consistent with my notes, I'm going to put a question mark here because I'm like, really, Mrs. Snipes, you could really estimate between gradations? And a lot of times when I put a question mark there, what we're really kind of saying is that's plus or minus oftentimes 0.01 centimeters. That's the wiggle I'm talking about. That's the uncertainty. You'd be like, well, Mrs. Snipes, when you use the scales, they just spit back. We have digital scales in there, and they'll just spit back a number. And they'll say it's like 5.003 grams. You'd be like, well, I know it's 5.003 grams. Ah, no. You know that there's uncertainty in that last digit. There's play in that last digit. And actually, and it's not necessarily this simple, but those balances are really have a tolerance or an uncertainty, a wiggle out there, okay, in that last digit. So when it says that all measured quantities, all measured values have error in them, and then it says that it is actually, it doesn't say there, but that if you, from left to right, where is the error? Where it's in that rightmost digit. It's in the little thingy, kind of. It's in the weeds. Okay. So this says you can report only one uncertain digit. Those question marks, those are my uncertain digit. Thou shalt not lie and say, for instance, if I was doing my little thing up there, my measuring thing, the ruler I have, that ruler I have now with the gradations I have, like if I put 44.587632 centimeters, you're like, are you serious? Because honestly, I have a tick mark for all of these. And this was my estimating. So I cannot do that. Okay? You're just lying. This is kind of in italics what I've been describing, that as a measured quantity is written from left to right, where is you only have one uncertain digit. Where is it? Well, it's in the rightmost digit. Because that's kind of the finest, the smallest, the unit. Makes sense? So not question marks, but kind of turned red. In these, the convention for these slides is anytime you see a red number, that's where the uncertainty lies. Okay. So I must have a measuring device, and actually you might imagine that kind of the more digits you have, the more expensive probably the equipment is. Okay. So in this case, the solid numbers are in the ones place, the tenths, the 100ths, the 1,000ths, and the uncertainty begins in the 10,000ths place. Thou shalt only have one uncertain digit. So keep that in mind. So this is measuring blue powder. This could have been our copper 2 sulfate. And I mentioned the gradations kind of with the ruler. To get your bearings, the 10 is 10 grams, so this would be what, 5 grams. So this is a little past 1 gram. And I mentioned you're going to be doing this in the lab. You have to estimate kind of between the gradations. So for that reason, up here, you can see why, what would you report this is? Well, the person, and I can kind of see why they got that, they said that it's past the 1 gram mark. It's kind of a crude scale, isn't it? Past the 1 gram, not to the 2 gram at all. And where is it? Well, about 2/10 along the way. So you can see at the top there, 1.2 grams. So you have to estimate between gradations. So there's uncertainty in the tenths place, but the 1 is up. Here's another one for you. This is kind of an interesting sort of way this works. Measuring a pistachio. And again, this is 1 gram, 2 grams, 3 grams. And so we are actually past the 1 gram onto the 2, but notice the gradations are tenths. So we're gonna actually push ourselves to the 100th place. So we get 1.12, so 1.2, and guess, so what would you think is kind of estimated between the 0.2 and 0.3? Sometimes there aren't the right answers. This person went like 6/10 of the way along between the 0.2 and the 0.3. So again, we're solid with the 1, we're solid with the 0.2, and the 0.6, you're like, you estimated. All right, so I think we'll stop there. It's good. We'll take a running start, but again, somewhat apologetic, but we need to finish this part, otherwise tomorrow's lab is not going to work for us. So we'll finish this part and then we'll do that. And you'll still be out here at time. Be careful out there. So the cool temperatures are tonight, tomorrow, and Wednesday, is that right?
Yeah, it starts warming up.
Now I will reboot the computer so it will be happy.